Okay, so what we practiced yesterday was going from moles of one compound in a stoichiometry problem to moles of another compound in a stoichiometry problem. And we did that by using just one parenthesis. And that parenthesis was always using moles on the top and moles from the bottom. And where we got those numbers from was the balanced chemical equation, right? BCE, balanced chemical equation. Well, most of the time in chemistry, we are not actually counting in moles, and we don't actually care about how many moles are formed. What we are more concerned about are quantities that we can actually measure. And certainly grams are the most accessible way to measure how much of a chemical that we have. Well, going from grams to moles, this is a skill that we mastered when we were in chapter 10. And we know that in order to go from grams to moles, we're going to need to use the numbers from the periodic table, right? The molar masses from the periodic table. And then to make a jump from moles to grams, again, we're going to use the molar masses, the numbers from the periodic table. And so mass to mass problems are the most common type of stoichiometry problems where we start with a known number of grams of reactant. We do one parenthesis to convert to moles of the reactant. We do a second parenthesis to convert to moles of a product. And we do a third parenthesis to convert to grams of a product. We could also do that exact same thing, but backwards. And it doesn't even necessarily need to be reactant and product. It could be two reactants, but it's always going to be from a known quantity to an unknown quantity. So let's look at the first problem here, right? I outline what are the three parentheses that we're going to use. Okay, so how many grams of water, circle the do, is produced from 14.87 grams of NH4NO3. That's ammonium nitrate. So we take the number that's given to us and we write it out front. 14.87 grams of NH4NO3. And the balanced chemical equation says that for 1 mole of ammonium nitrate, I will make 2 moles of water. So in order to do this problem, I'm going to need to convert everything into moles. So the first thing I'm going to do is convert from grams of ammonium nitrate to moles of ammonium nitrate. I'm going to look on the periodic table and find the molar mass of ammonium nitrate. So that's going to be 2 nitrogen, 4 hydrogen, and 3 oxygen. And when I add those up, I get 80.052 grams of ammonium nitrate. That's the mass of 1 mole of ammonium nitrate. Okay, so that's my first parenthesis, is always converting from grams to moles. Now that I have moles of ammonium nitrate, I'm going to convert to moles of water. And when I go from moles to moles, I'm using the coefficients from the balanced chemical equation. So the coefficient in front of ammonium nitrate is 1. So 1 mole of ammonium nitrate will produce 2 moles of water. And if I stopped the problem right here, my answer would be in moles of water. But remember, the question, when I circled the do, asks me for grams of water. So I need one more parenthesis where I convert from moles of water to grams of water. And that is using the molar mass of water, which is 18.016 grams. Right? Look at the rules of dimensional analysis that I have followed so that the unit out front matches the unit down bottom so that they will cancel. Right? The unit over here, moles of ammonium nitrate, cancels out with this moles of ammonium nitrate. Moles of water cancels out with moles of water. So the only unit that is left now is grams of water, which is what I actually wanted. Numerically, I plug this into my calculator all in one step. So in my calculator, I'm doing 14.87 times 1 divided by 80.052 times 2 divided by 1 times 18.016 divided by 1. Anytime that I'm multiplying or dividing by 1, I can actually, you guys know, not put that in the calculator just to save time. My answer comes out to 6.693 grams of water, right? 4 significant figures. Any number that comes off the periodic table always carries with it 4 significant figures. And any of these 1 mole or 2 moles, those weren't measured with an instrument, so I don't worry about them in terms of significant figures. So yeah, my answer has 4 significant figures there. Okay, let's do another problem using these 3 parentheses again. How many grams of ammonium nitrate are needed to produce 249.6 grams, and that's dinitrogen monoxide, right? This is a covalent compound, all nonmetals, so I have to use prefixes when I name that. So I take the number that's given to me and I write it out front. 249.6 grams of N2O. First parenthesis is always converting to moles. 1 mole of N2O. I look on the periodic table, 44.02 grams. Next parenthesis, I convert from moles of N2O to moles of NH4NO3 using the coefficients from the balanced chemical equation. So the coefficient in front of N2O is 1 mole of N2O. And the coefficient in front of ammonium nitrate is also 1. So 1 mole NH4NO3. The question's asking for grams of NH4NO3. 1 mole of NH4NO3. And we already found the molar mass in the previous problem. That's that 80.052 grams. Plug this in my calculator, right? I just go from parenthesis to parenthesis to parenthesis. Multiply by the top, divide by the bottom. 4 significant figures. The number out front has 4 significant figures. All the numbers from the periodic table carry 4 significant figures. And I get 453.9 grams of NH4NO3. One really common mistake that students make is, when do I use the numbers from the coefficients of the balanced chemical equation and when don't I? And so I really want to make that clear that the only time we are ever using the coefficients from the balanced chemical equation is in that center mole over mole parenthesis. Every other time when we're converting from grams to moles in the beginning or moles to grams at the end, the number in front of the word mole is always 1. It doesn't matter what it is in the balanced chemical equation. So right here in number 3, I said 1 mole of water has a mass of 18.016 grams. That is the true conversion factor. Even though in the problem, the coefficient of water is 2, because in this particular balanced chemical equation, 1 mole of ammonium nitrate will make 2 moles of water, but that doesn't change the molar mass of water. So that's a real common mistake that students make. The beginning and the end parentheses with moles and grams should all just have 1 mole. It's only the mole over mole parenthesis that has the coefficients. So we're going to do a couple more of these problems before you do your homework. And these next two, numbers 5 and 6, are using a BCA chart. And again, you don't need to do these problems with a BCA chart, but I'm showing them this method because it does become easier when we start doing more complex problems. So, how many grams of lead 2 iodide will be produced from 149 grams of potassium iodide? So the chart that I made looks exactly the same as it does before, BCA, before, change, after, but I put a row on the top in grams and a row on the bottom in grams because this problem gives me grams of potassium iodide at 149.0 grams. The question is asking about lead iodide. I start out with no grams of lead iodide. So the first thing I need to do is figure out, well, how many moles is that going to be? So I need to convert the 149 grams of potassium iodide to moles. I look on the periodic table and the molar mass for Ki, 1 potassium, 1 iodide is 166.0 grams. And when I do out that calculation, I get 0.89759 moles. So right now I'm starting out with 0.89759 moles of Ki. When this reaction takes place, all of that potassium iodide gets used up. So the change row is always going to be plus or minus. In this case, it's going to be minus 0.89759. So I use up all those moles of potassium iodide, and those are going to be used to make some amount of lead iodide. Well, how much lead iodide? This is where I'm going to use the coefficients from the balanced chemical equation. So I'm going to take that 0.89759 moles of potassium iodide, and using the coefficients from the balanced chemical equation, 2 moles of potassium iodide will make 1 mole of lead 2 iodide, right? I'm saying lead 2 iodide because lead is functions as a transition metal. So I need to use the Roman numerals there. So 0.44879 moles of PbI2 will be made. So 0.448795, and right, I started with 0 moles. Now I've added this 0.44 number, so afterwards I would have 0.448795 moles. Check what the question is asking. It's asking for grams. So now I need to convert that 0.448795 moles of lead 2 iodide to grams, right? 1 mole, and then the coefficients from the the molar mass from the periodic table, this is a big one, 461.0 grams. What does that come out to be? That comes out to be my answer here, which is 206.9 of lead 2 iodide. So that's my answer right here. Right? The only time that I use the coefficients from the balanced chemical equation was in my mole over mole parenthesis. Okay, we're going to do one more problem like this. If you want, you can try number 6 on your own, like pause the video right now, try number 6. You can do a BCA chart, or you can just do, like, that's why I left you this space. If you just want to use this space to do 3 parentheses, like we did on numbers 3 and 4, do that, or you can try the BCA chart. Okay, so pause this right here, try this number 6, and then unpause to see how you did. So this problem here, how many grams of potassium nitrate will be produced if 54.6 grams of lead 2 iodide are also produced? So this is, the reaction has happened, and after I have 54.6 grams of PbI2. And what I want to know is, well, how many grams of potassium nitrate will also be produced? So the first thing that I'm going to need to do is obviously convert grams into moles and then figure out, well, how many moles of potassium nitrate will also be made, and then convert that to grams. So I'm going to start with that 54.6 grams of PbI2, convert to moles, 461.0 grams per mole. I got that number off the periodic table, and this comes out to be 0.11757 moles of lead 2 iodide. So this is, afterwards, I have 0.11757. I started out with none, no grams, no moles. So that means I must have increased my number of moles of PbI2 by 0.11757. How do I go from moles of PbI2 to moles of KNO3? Well, if I'm going from moles to moles, I'm going to use the coefficients from the balanced chemical equation. So 0.11757 moles of PbI2. According to the coefficients from the balanced chemical equation, 2 moles of potassium nitrate are made for every 1 mole of PbI2. So I just take that number and I multiply it by 2, and that's where I'm going to get that when I start with no grams of potassium nitrate and no moles of potassium nitrate, I will increase by 0.23514 moles of Ki. And then, of course, to go from 0.23514 moles of, it's not Ki, it's KNO3. Potassium nitrate to grams, 1 mole of KNO3 has a mass of 101.11 grams. My answer for that is 23.8. Right, so 0.23514 moles of potassium nitrate will have a mass of 23.8 grams of potassium nitrate. And you could have done that in 1 3 parenthesis stoichiometry problem like we did in numbers 3 and 4, and your 3 parentheses would be this parenthesis, then this parenthesis, and then this parenthesis. Putting it in a chart like this, for some people, makes it easier to understand what's going on. For some students, it makes it harder to understand what's going on. So that's fine. All you need to do is do whatever it makes more, or makes the most sense to you. So for your homework for this, here's the homework packet here. Yesterday you did numbers 1, 2, and 3. So now you're going to do all the mass-to-mass problems. So 4, 5, 6, 7, 8, 9. So try these 5 gram-to-gram problems. You don't need to do it in a BCA chart, or you don't need to do some of them with 3 parentheses. You can do whichever one of the 2 methods we have looked at. Okay, so either one works. Good luck, and we will go over the answers to these next week if you have any questions.